My name is Xavier Medina. I'm here with my teammates Fernando Lopez and Gianfranco Pisani. Our faculty advisor is Dr. George Dooley Kravich.
For our project, we want to optimize the compressor blades of turbochargers. So for that, we want to vary the shapes of the blades in the turbochargers to improve the flow. We're going to be using the Mitsubishi TD04 compressor housing in order to house our compressor wheel. Our project objectives are to improve the pressure rate. When I say this, the pressure ratio is the difference between the inlet pressure and the outlet pressure. We also want to improve the engine efficiency with the use of our turbine blade. And we also want to create a CNC model of the blade, of the wheel, of the compressor wheel. Here's a video of the compressor and the housing working together. Our design objectives, we want to have a high efficiency on the operational range of the turbo, of the compressor wheel, because they have a specific RPM where the compressor wheel is able to create the difference in pressure. We also want to reduce the internal combustion inside the housing. We want to reduce the turbo threshold and the lag inside, when the turbo is operating. Here's our blade design. At the moment it has only 10 blades. We're not sure about how many blades we want to use. This will depend on the results from the simulation. And here's a representative cutaway of the compressor housing and the compressor wheel.
Okay, so the grand scope of our project is the optimization of the blade design. So we're going to basically design different blades and we're going to change the parameters. We're going to change different twist angles. We're going to change different locations of our line, of our 3D line that we're going to make. These different designs are going to be put through a computational fluid dynamics analysis, and then they're going to be validated through different results through a convergence study. The optimization process will continue and it will be repeated. It's shown right here. So we're going to create a model, a design. We're going to analyze the data. We're going to validate it, and we're going to optimize it. And we're going to continue for several iterations. So for our global components, turbochargers are used very frequently in cars nowadays. The market is tending to downsize their engines, and they're starting to include turbochargers. Diesel engines as well, they're starting to become more and more popular, and they tend to have a turbo as well. Here are a few figures about where the market is going. Here's a trend. There's an increase of 80% from 2012 to 2017. This is a study that was created by Honeywell. They are a major player in the market today. They own about 60% of the market. Here's a timeline of our project. Right now we're still in the CAD modeling phase. We have to create a lot of designs, so it takes a lot of time for us to do that. That's why the majority of our project is in that area. Here's a cost analysis. It's just an estimate. The majority of our cost is going to be in the computing. So it's going to take a lot of hours to run the different meshes and run the different analysis. All right, so as you can see here, we have 3 different methods to choose from when it comes to manufacturing our prototype. We have injection molding and casting, which for mass production, it is beneficial. But for our project's application, we are going to decide with going with CNC modeling, since we plan to probably make 1 and possibly 2 prototypes. Now, we're going to be modeling from an aluminum billet, and we are going to be using CNC modeling also due to the fact that it's on-site, it's available for us, and we can go ahead and allow ourselves to have machining practice. Now, the designs, we want to go ahead and first test them through computational fluid dynamics, then run them through the optimization program to make sure that we have our optimal design. Once we finally choose our final design that we're going to go ahead and prototype, we will go ahead and start running it with an electric motor just to check for clearances, make sure that there's not too much play, not too much rotational vibration, and make sure that the turbo can withstand pressure. Also, our ultimate goal will be to finally create this prototype and fit it into our team member's current turbocharger that is already fitted in his car and have real world performance data. So to conclude, we're going to be optimizing the blade design. We have to always keep in mind that the Mitsubishi TT04 turbo housing are constrained. We're going to have all the create many designs, run CFD analyses, and then optimize each one. And global component, there's a big market, and so it optimizes our growth and means that we will always have demand for it. We would like to acknowledge our advisor, Dr. George Zulikravich, and also members of the Maynard Laboratory. Thank you very much for your attention and your time. Very good.
Thank you.
Any questions?
I got a question. You guys are going to do some measurement and testing on this, right? So do you have any idea of what your success is going to be, your target is going to be for enhancement of the optimization?
Our target for that we're looking for is at least like a 5% efficiency increase in pressure ratio and increasing our range, our working range. So different RPMs, we have different efficiencies. So we want to increase the threshold where our efficiency is at its greatest.
As compared to what?
As compared to the base turbo, the TD04 turbo compressor. Yeah, we're using the housing. We're not optimizing our housing.
So are you going to have data from the existing turbo and the new turbo?
Yes.
Give us a
Yes.
relative relation.
It's not the complete turbo, it's just the compressor wheel that's gonna be the difference of the whole system.
Yeah, we're going to compare the two, and hopefully we can get results that improve our compressor.
So you're going to try to get 300 horsepower out of a 200 horsepower engine?
Well,
That's another point of view.
That's another
because,
point of view.
We can make more power, or we can create the same amount of power easier.
One question I want to throw at you, because I saw the iteration. I like the idea of your iteration, but I suggest that you use something like a design of experiment to be able to first figure out what variables you're going to change, and then set up a DOE in order to do that iteration pathway. Because if you don't, you're going to end up in a situation where you may start iterating and it's never going to relate.
it's never going to converge.
You're never going to know where or what to change to have the most impact.
Yeah. Well, as it was said before, in the optimization process, we do have a certain number of parameters that we are going to choose. So we're gonna have to measure the current turbo that we have in our team members and get the information from their performance statistics. And we're gonna go ahead and see what parameters we can change and definitely play with to optimize our design.
So you're going to have to do the experimental work on the baseline first?
No,
before you
we're
can
actually
start
going to
design?
create a completely new blade from scratch. So
No, but-
we're going to create a new blade from scratch.
But to know where your baseline is, you're going to have to get that before you start this iteration.
Right? Yeah.
Yeah, that makes sense.
I think so.
Does the data?
That's a watch out, because
We're gonna get the data
classically,
from the.
you're not going to want to do your design if you had all the time in the world, you would test, design, test.
Right.
But you're not going to have that time.
Yeah.
And actually, I noticed from your project plan, are you planning to be done by the end of the summer?
By the end of the summer, not in terms of completely everything. We want to be able to already have quite a few designs and evaluate
Because your timeline ended in August, that's why I asked. the
Yeah,
question.
it ends it's the 25th of August. Yeah, I put it like that just to, because the computing time, we don't know exactly how much time it'll take, if it'll be done separate days, if it'll be done all in one day.
But
Because
Dr. Carnegie, are they?
No,
There's
well,
no
I'm gonna
summer
jump in here.
graduation.
Don't you have a fall session for senior design too?
yeah.
So should your schedule not go to December?
Mm-hmm.
And what do you plan, this question is, what are you planning on doing from August to December?
You're all done?
Finished?
We would really like to be done
Yeah,
as
we
early as
would, but
possible, as
no,
soon as
that-
possible, because the machining process is what's going to be the last step, is going to be the hardest step for us.
Do you have a 5-axis machine here?
No, you have
No, we have, I'll be working with a the shop that they use is not a 5-axis, but there are ways to manufacture it. I mean, you just need to have the billet, and when the tip comes down, you can make different kind of patterns in order to do the blades.
You need to find a 5-axis machine to make those work, right?
We don't have.
Well, if you have someone that would know.
You have one that can
You can use your help to.
You have one that,
You have to have a rotary table and you have to program it.
Those are challenges that we.
When you get it all designed,
Surprise.
throw it, we've probably got a couple of machinists that would like to play with you.
Okay, okay.
so you got a full sponsor.
We'll see you
Flashing
after.
light here, guys. He's helping.
You got a full sponsor.
He's got the ability, capability.
Any more questions?
More questions? Atendido.
Okay.
Thank you very much.